Section 2-6, the intermediate value theorem and the extreme value theorem. The objective of this section is given a function, determine whether it meets the conditions of the theorem, and then use the conclusion appropriately. Throughout the course of the year, we'll come across several theorems. It's important that you know the theorems first of all and know them by name. It's extremely important that you understand what the conditions are for that theorem and can show that you meet all of those conditions or that you don't meet them, whichever the case may be. But if you meet them, that you understand what the conclusion of the theorem then guarantees you as well. So let's take a look at the basic structure here for theorems real quick, and then we'll take a look at these two theorems in particular. Most theorems that we're going to see throughout the course will be structured in this form right here. It's what we call an if-then theorem, where you have if followed by some conditions. Most of the time we're going to see it's multiple conditions that we have to meet. In some cases it might be just one condition. And then you have then followed by the conclusion. And the basic structure here indicates that you have to meet the conditions in order for the conclusion to also be true. Now there's other types of theorems we'll look at as well later on, but for right now we're going to just focus on this type, an if-then theorem. So then the way that you use the theorem is this. If you can show that you meet all of the conditions, if all the conditions are true, then the conclusion must also be true. That's what the theorem guarantees. If you meet these conditions, it guarantees that this conclusion is true. On the other hand, if any one of the conditions are not true, if they're not met, then you don't know what that means about the conclusion, actually. The conclusion could be true or it could be false. The conclusion may or may not be true. That's a common misconception there about an if-then theorem. We're really good at knowing that if I meet these conditions, that guarantees the conclusion. But we're not very good at the second part here, that sometimes we want to say, if we don't meet the conditions, that means that the conclusion can't be true. It's not what an if-then theorem says. It says if you don't meet all the conditions, then we don't know for sure what that means about the conclusion. It may be true in some cases, it may be false in other cases. Okay? So let's take a look at this first theorem here, the intermediate value theorem. We'll call this the IVT for short, standing of course for intermediate value theorem. All right, for the intermediate value theorem, there are two conditions that you have to meet. I have to show that I meet both of these conditions before I can know for sure that the conclusion is true. And again, what we just said earlier is just because the conditions are not met doesn't mean that the conclusion can't be true. The only way for me to guarantee the conclusion is true to show that I meet both of these. So it says two conditions here. If, first of all, f is a continuous function on the interval from a to b, and that's what we call a closed interval. Notice that we use brackets here, square brackets, to indicate it's a closed interval. And a closed interval means that it's the interval that includes the endpoints. So it's the interval from a to b including a and b. That's the first condition. Deals with continuity. The second condition is that y, which is going to be some number that we're going to pick, y is a number between f of a and f of b. So we have to pick a y value that's basically between the endpoints of our function, f of a and f of b. So if I meet both of those conditions, the theorem guarantees me the following conclusion. It says then there exists a number C on the interval from A to B, and it's an open interval in this case. Notice that we use parentheses. This is called an open interval. And it's called an open interval because the fact that we are not including the endpoints. So the parentheses there indicate that it's all the values between A and B, but not including A and B. So in other words, C will not be at A or B, but it's going to be somewhere in between. There exists a number C on the open interval from A to B, for which f of C is equal to y. So in other words, it guarantees us that this y value that we've picked, there is a corresponding x value that when I plug it into my function, that f of C is equal to y. Now, that might be a little bit tricky to read through and figure out exactly what it's saying. So let me draw you a picture of a graph here that represents this function really well. Now, there's lots of functions, by the way, we could sketch here to illustrate this. I'm just going to sketch one that looks something like this here. We'll say that this is f of x. And let me pick this point right here will be our starting value at A. And let's pick this point right here as B. So that corresponds then to these 2 points on my function. So in other words, this is the value f of A. And this is the value of f of B. All right. Now, the first thing that our theorem says is that we have to have a function that is continuous on the closed interval. That's what I've got here. I've got a sketch of a function that's continuous from A to B, including at A and B. The second condition says that I have to pick a y value that's between f of A and f of B. So I'm picking a y value somewhere in this range right here. Somewhere between f of A and f of B. So I'm just going to pick a y value here. We'll call this y right here. And as long as I have a continuous function and I have a y value between f of A and f of B, the conclusion of that theorem guarantees me that there has to exist some number C between A and B here, from here to here somewhere, such that if I plug that number C into my function, I end up getting this value of y. Probably the easiest way for me to illustrate that is just simply draw a dotted line from y going across here. That's the y value we're talking about. And the function, or the theorem guarantees me that there's some value. In this case, I'm going to pick this point right here. Some value C, such that if I plug C into my function, that I end up getting y. In fact, this would be the point C, f of C. The y value there is equal to f of C. Now you'll notice that there's actually a couple other points between A and B where this occurs. There happens to be one right about here, really close to A. There's another one right here, really close to B. The theorem doesn't say anything about having more than one. It only guarantees me that there is one. But you can see that it is possible to have more than one. All right. You'll also notice that there are places like, for example, right here, where the function is still continuous, of course, and that I know that there's a C value that I could plug into my function to get those corresponding y values. But because that's below f of b, these are all below f of b here, the theorem doesn't talk at all about those values. Same is true if I continue f of a all the way across here. Same is true for this little spot right here. Even though my function is continuous still there, even though I know that I can plug in a C value into my function and get those y values, it doesn't say anything about those because of the fact that those are outside of this range from f of a to f of b. All right, so that's the theorem. I think it's pretty straightforward what it's saying. You got a continuous function. You pick any y value in a certain range there between f of a and f of b. and you're guaranteed there's a corresponding x value you can get to get that y value. All right, let me show you an example of a common use of the intermediate value theorem. It can be used for a number of things, but this is a common use of it. So show that f of x has a root on the closed interval from a to b. Now, a root, of course, it's another word that we use to describe a zero or an x-intercept. Root, zero, x-intercept, those all mean the same thing. So let me show you how we could do that. I'm just going to do this with a sketch of some function here. Again, it doesn't really matter what our function looks like, but I'm going to draw some function that looks like something like this. And let's assume that this is a over here. So that corresponds to f of a being down here. And let's say that this is b right here. So that corresponds to this value being f of b right here. All right, you'll notice that first of all that at x equals a, the function is below the x-axis. So that means that f of a is actually less than 0. And you'll see that at the other end, at b, f of b is above the x-axis, so that means that f of b must be greater than 0. So a value that's less than 0 on one side, a value that's greater than 0 on the other side. So to use the theorem to show this, I have to have, of course, first of all, a continuous function, which I have here in the closed interval from a to b. I then have to pick a y value somewhere between f of a and f of b, so that's somewhere in this range right here. So I'm going to pick a y value, since I'm looking for an x-intercept or a root or a 0. I want the y value to be on the x-axis there. That's where y equals 0. So that's right down here, right down the x-axis. And in fact, I can see the point now that the theorem will guarantee, again, I've got a continuous function and I've got a y value between f of a and f of b. So my conclusion of the theorem says I'm guaranteed there's some point c, which turns out to be right here, such that f of c is equal to y. F of c is equal to y, which we said y was going to be 0. So we're guaranteed that f of c is equal to 0. In other words, it's a root. It's a 0. It's an x-intercept. That's a common usage of the intermediate value theorem, showing or guaranteeing that you know that there's a root or a 0 of your function at on some interval. All right, let's take a look at an example here. Example 1 says if f of x is equal to the following. Let me just go ahead and write our function down. X cubed minus 4x squared plus 2x plus 7. It says use IVT to conclude that a value of x equals c occurs between 1 and 3. So we're talking about the interval from 1 to 3 here. I'll go ahead and add that to our function. We're restricting our domain in essence just to that interval, for which f of c is exactly equal to 5. So the y value that they're telling us to use is y equals 5. All right. All right, so let's see if we can show this using intermediate value theorem. And I'll start out with just saying IVT. That's kind of a nice way to start out here, that you indicate what theorem you're going to use to prove this, even though they said at the beginning to use IVT. Still indicate clearly what theorem you're using. And then remember that you have to show that you meet all of the conditions of that theorem first. You can't just automatically assume the conclusion is true. You got to first show that you meet the conditions first. So the first condition is about continuity. Are you continuous on the closed interval, in this case from 1 to 3? Well, if you go back and look at what function we're working with here, it's a polynomial function. And polynomial functions, actually in a previous section here, it goes back to section 2.4 where you dealt with continuity. One of the problems that you worked on was proving that polynomial functions are continuous. So you've already done the work for this, in other words. F of x is a polynomial and thus continuous for all x. We only need to be continuous from 1 to 3, but we were guaranteed by that we were continuous for all x. So we have continuity. So the answer to this first question is yes, we are continuous. 1 down, 1 to go. The second condition deals with picking a y value. Now they told you to use the y value of 5. And I have to show that that y value of 5 is between f of 1 and f of 3. So really all I got to do is plug in 1 and 3 into my function. And to do that, we'll just punch this into our calculator just to make this a little bit easier. We're going to need this equation in a second anyway, so it'll make sense for us to put it in right now. But in y1, we'll punch in x cubed minus 4x squared plus 2x plus 7. And I guess you could find those two y values several ways. You could actually graph this thing, or you could go back to your home screen and find y values that way using your function notation. I'm just going to use the table, I think. And I'll set it up in ask mode. And I'll just go to my table and punch in the two values I want. I want to know what y1 or f at 1 is equal to and what y1 or f at 3 is equal to. So they're equal to 6 and 4 respectively there. So we have f of 1 then was equal to 6 and f of 3 was equal to 4. All right, and so obviously we can show that y is between them. Thus y equals 5 is between f of 1, which equals 6, and f of 3, which equals 4. So now we can make our conclusion. Thus, by the intermediate value theorem, we can just write our conclusion here, which is basically taking the same conclusion from the theorem itself. Thus, there exists a value of c on the open interval from 1 to 3 such that f of c is equal to that y value of 5. Notice it doesn't tell us how to find that y value or what the y value is, or excuse me, the c value. It doesn't tell us how to find that c value or what it is equal to. It just guarantees us that it exists. There is some c out there for which that's true. All right, take a look at the second part of this. The second part says to find an approximation for this value of c numerically. And by the way, I don't think you want to even attempt to do this any other way than numerically. When they say do it numerically, they're talking about using your calculator to get a numerical solution. If they said do it algebraically, that means you got to work out the algebra to solve an equation. That'd be a lot more difficult here. But basically what they're saying here is to solve the equation f of c equals 5. F of c is the function that we have above with c substituted in, and solve that for where it's equal to 5. Probably the easiest way to do that numerically is to do this graphically. And so I'm going to go to my calculator here, and I guess we'll use an appropriate window here for what makes most sense. You could do this in the standard window here, but I'm going to change the window up slightly. They gave us a sketch of it in the book too that we could use, but if we go from 0 to 4 for our x's, if you're not sure exactly what y values to use, in this case I know it has to be between 6 and 4 because that's what f of 1 and f of 3 are. But if you didn't know that, you could use your table to help you come up with an appropriate window. I'll start out my table at 0 and have it change by 1, put it back in auto mode, and it will just give me a list of y values that my function is going to take on. So it looks like if I go from like 0 to 15 here, it'll be a pretty decent window for the y's. More than I need for sure, but That will be sufficient. And then in y2, I want to put in y equals 5. All right, because I'm trying to find out where my function is equal to 5. So let's graph that. And basically what I'm looking for here is the intersection of this line y equals 5 and my function, my polynomial function. You'll see that it crosses here in more than one place. In fact, if I had this in the standard window, you'd actually see that it crosses it 3 times. And the one solution that we're looking for is the one that's between x equals 1 and x equals 3. So don't get distracted by other solutions here. We're only looking for the one between 1 and 3. You could set your window up to only go from 1 to 3, so that's all you'd see. But I wanted to show you that you can potentially have more than one solution to this, but only we're only going to be guaranteed one on the interval from 1 to 3 in this case. So we'll calculate the intersection. Go to Second, Calc, Second, and then your Trace button. We want to find the intersection. You pick your two curves. Just press enter on those. The guess, it's asking you for approximately where the intersection occurs at. And if you're not close enough to the right intersection, it'll in this case find the other one, which you don't want to do. So we get x is 1.311 is the value there. So we'd say, in this case, that c is equal to 1.311. And that, by the way, is sufficient work. The work here is to show me what equation you're setting up and solving. So I'm taking f of c and setting it equal to 5. And then your solution is, of course, the value the calculator gives you. So this is sufficient work, and this is our solution, okay, or our answer. All right, there's one more theorem that actually is shown in this section. It's actually a part of one of the problems that you're going to do. It's problem 13 that you'll do in this section, but it's called the extreme value theorem. And the extreme value theorem, or we'll call it EVT for short, says this. There's only one condition here, but I still numbered it just so you can see the number of conditions that you have to be met. And we'll do that basically for every theorem in here. We'll number how many conditions there are, just so it helps us remember how many things we have to show that are part of the conditions. So it says if, first and only thing here, f is a continuous function on the closed interval from a to b. So it has the same first condition as your intermediate value theorem. And that's the only condition. So if you have a continuous function, you are guaranteed the following, and it has to be a continuous function on a closed interval is the other part to this. All right, extremely important that it's a closed interval. Then the conclusion is there are two values. There exist two numbers, C1 and C2, on the closed interval. Notice this time it's a closed interval. C1 and C2 could occur anywhere between A and B, including perhaps at A and B, for which f of C1 and f of C2 are the minimum and maximum values of f of x on the interval. This is why we call it an extreme value theorem. Extreme values referring to a minimum, the smallest value, and a maximum, the largest value. Extreme value theorem, talking about maximums and minimums. All right, again, let me draw a picture of a function or a graph of a function to help represent this for us. And there are lots of functions that we could sketch that would illustrate this, but I'm going to kind of draw a function similar to one that we saw earlier. And we'll say that this right here is A. And we'll say that this right here is B. And so the theorem says this is f of x. If I've got a continuous function on the interval from a to b, which I've got here, on the closed interval, including a and b, it guarantees that at some point I hit my lowest value, which actually turns out to be pretty close here, but when I look at the lowest value, looks like the lowest I get is right here. This value right here looks like it's the lowest. You can compare it with all the other y values that you see between a and b, but that looks like that's the lowest. In fact, if I continue this across here, it's definitely the lowest y value. So this would be called C1, and they don't distinguish between whether C1 is the max or the min, or the same is true for C2, so it doesn't matter which one you call C1 and which one you call C2. So in this case, C1 would be right there. And it also guarantees me another point called C2, that's the maximum. And the maximum, it looks like, is actually at this endpoint right here. And again, you could draw a line going across here, just kind of verify that there's no other place where my function gets above that point, which it is not. So in this case, it turns out that C2 is at A. So A is also equal to C2. Doesn't have to be that way. It just turns out to be, in this case, it is. All right. So on any continuous function on a closed interval, you're guaranteed that it hits a high point and a lowest point. And that is the end of this section here.